Good afternoon, and welcome to the 6th week of the facilitation on solid state physics course. This is 407. So far we have discussed the concept of dielectric properties of solids, and also we discussed extensively last week the magnetic properties, where we discussed about their magnetism, paramagnetism, and ferromagnetism. So also we briefly discuss some concept about antiferromagnetism. So this week, which is the 6th week, we shall be looking at magnetic resonance. So where we are going to be looking at nuclear magnetic resonance and the applications in the medical field, then ferromagnetic resonance and antiferromagnetic resonance. So if you have any questions in all the things we have discussed so far, any questions whatsoever, you are free to ask me before we proceed to the next thing we are discussing today. Have any questions? Any question? Okay. In the absence of no questions, so I will briefly recast what we discussed about antiferromagnetism before we move to the next thing. So last week, when we were discussing ferromagnetism, I told you that it is a phenomenon in which all the spins in these materials align in one direction. But in the case of antiferromagnetism, they are aligned anti-parallel to each other. One is pointing up and the other is pointing down. So we say the physical origin of one field is in the quantum mechanical exchange integral. So it can be shown that the energy of interaction of atoms I and J bearing spins xi and sj contains a term that is exchange energy, which is equal to -2 jxi dot sj. Excuse me, please. The 2 in this expression is just to cancel out double counting. So where J is the exchange integral and is related to the overlap of the charge distribution I and J. So when the exchange integral J, that is the one we have in equation 2.4, is positive, we have ferromagnetism. When J is negative, we have antiferromagnetism. So more or less, this equation is used to describe properties of materials in terms of either you have a materials that you don't know if it is antiferromagnetism or a ferromagnetism in nature. So if the exchange integral is positive, so automatically the materials will give you a negative exchange energy. So if it is negative, it will give you a positive exchange energy, and that implies an antiferromagnetic system. So in materials that exhibit antiferromagnetism, the magnetic moment of atom or molecule, usually related to the spins of electrons, align in a regular pattern with neighboring spin pointing in opposite directions, like I said the other time. So it's aligned opposite to each other, so anti-parallel to each other. So some simple questions that you can try to solve on your own is somebody can ask you, can you differentiate between ferromagnetism and antiferromagnetism? And also, somebody can ask to explain in terms of exchange integral ferromagnetism. I just discussed that now. So we also have some materials known as ferrites. So they are magnetic in nature. They are found in the interior of the heart. So ferrites of magnetic intellect belong to the group of compounds represented by the chemical formula this, where M is a divalent metal ion such as manganese, cobalt, nickel, and copper, magnesium, zinc, cadmium, and iron 2, or a mixture of these ions. So these are good examples of material that possesses magnetic properties. Now let's look at magnetic resonance, which is the bone of contention for today's class. So in this discussion today, we shall be discussing dynamic magnetic effect, which is associated with the spin angular momentum of nuclei and of electrons. So the information can be obtained about solids by resonance study, may be categorized as follows. Now, if we use magnetic resonance principles, we can deduce what we know as electronic structure of single defect. So in this case, we consider what we call a structure of fine structure of absorption. We also look at motion of spins or of the surrounding as revealed by change in the line width. So internal magnetic field can also be deduced using magnetic resonance. Now, if you are using nuclear magnetic resonance, which is called NMR, these are very useful materials in the medical field. So it's a physical phenomenon in which magnetic nuclei in a magnetic field absorb and re-emit electromagnetic radiation. This energy is at a specific resonant frequency, which depend on the strength of the magnetic field and the magnetic properties of the isotope of the atoms. So underline that word, magnetic field, the strength of the magnetic field and the magnetic properties of isotope of the atoms. So in practical applications, the frequencies is similar to UVH, like the one we have in television, and VHF, so which fall within 60 to 1000 megahertz. So NMR allows the observation of specific quantum mechanical magnetic properties of the atomic nucleus. So many specific techniques exploit nuclear magnetic resonance phenomena to study molecular physics, crystals, and non-crystalline materials through NMR spectroscopy. So nuclear magnetic resonance is also routinely used in advanced medical imaging techniques such as magnetic resonance imaging, MRI. So all isotopes that contain an odd numbers of protons or of neutrons have an intrinsic magnetic moment and angular momentum. In other words, a non-zero spin, while all nuclides with even numbers of both have a total spin of zero. The most commonly studied nuclei are deuterium and carbon-13, although the nuclei from isotope of many other elements, that is hydrogen, lithium, boron, nitrogen, oxygen, fluoride, sodium, silicon, phosphorus, chloride, chlorine, candium, and xenon, and platinum have been studied using advanced technique of NMR spectroscopy. So all these are just some of the things that we can use nuclear magnetic resonance to investigate. So now, a key feature of NMR is that the resonant frequency of a particular substance is directly proportional to the strength of the applied magnetic field. So it is this feature that is exploited in imaging techniques. If a sample is placed in a non-uniform magnetic field, then the resonant frequencies of the sample nuclei depend on where the field they are located. Since the resolutions of the imaging technique depends on the magnitude of magnetic field gradient, many efforts are made to develop an increased field strength, often using superconductors. The effectiveness of NMR can also be improved using hyperpolarization or using two-dimensional, three-dimensional, or higher dimensional multi-frequency technique. Now, the principle of NMR usually involves two sequential steps. Take note of these 2 points. The alignment, that is polarization of the magnetic nucleus spin in an applied constant magnetic field, H naught. Then the perturbation of this alignment of the nuclear spin by employing an electromagnetic, usually radio frequency, pulse. So the required perturbing frequencies is dependent upon the static magnetic field and the nuclear of observation. So that's concept of nuclear magnetic resonance. So the magnetic moment in this can be computed using this formula stated in equation 2.41. So in this case, uh, gamma is a constant known as magnetogeric ratio. By convention, I, which you are seeing there, denote the nuclear angular momentum measured in unit of hertz. So the energy of interaction with the applied magnetic field mu is given by equation 2.42. By the time you substitute this, then you have equation 2.43. So putting all these concepts together, we derive equation 2.44. All this one, you can solve it yourself by just putting the value of I to equals to half, then doing a kind of simple algebra analysis, you arrive at this equation 2.44. This is the fundamental condition for magnetic resonance absorption. Any question on that? It's a story concept which you can read and understand. Then the next thing we are going to be discussing is ferromagnetic resonance. So now, let us summarize the unusual characteristics of ferromagnetic resonance. One, the transfer susceptibility component, psi1, psi2, are very large because of magnetization of a ferromagnet in a given static field is very much larger than the magnetization of electronic or nuclear paramagnetic in the same field. Two, the shape of the specimen plays an important role because the magnetization is large, the demagnetization field is large. Three, the strong exchange coupling between the ferromagnetic electrons tend to suppress the dipolar contribution to the line width so that the ferromagnetic resonance line can be quite sharp, that is less than 1 giga, under favorable condition. So saturation, the fourth one now is the saturation effect occur at low RF power level. Now, if you consider this a specimen of a cubic ferromagnetic insulator in the form of an ellipsoid with principal axis parallel to XYZ axis of a Cartesian coordinate system, then we can have the internal magnetic field BI in terms of all these axes as BX, BY, and BZ written in this form. So if we try to introduce the Lorentz field